Just a quick note, this video was originally given as a live online class and has been edited and condensed for clarity. All right, so let me explain what we're doing. So the first thing that I want to start with is up until now, we have been doing these very simple counters. And counters are a type of what we call finite state machine. So I'm going to write a definition for you. So FSM does not stand for Flying Spaghetti Monster. It stands for Finite State Machine. And what does this mean? So let's give a little definition. So if you want a definition, it's a system that moves deterministically. So this is an important word. Between a finite set of states. Okay, so let's break it down. Okay, so what does it mean when I say deterministically? So what that means is, so I'm going to write down a definition. So it means that if I know the values of this, if I know the values of all the variables in the system at any one time, I can determine the next state. I can determine what it will be in the future. Okay, so what variables do we have? So we have not looked at inputs to the system. So counters, right? They don't have inputs. They're just like cycling mindlessly through the same set of states. But we today are going to look at an example of a system. It is still going to be a counter, unfortunately. We will move on from counters eventually, I promise. But it will have an input. Okay, so if I know the values of the inputs to the system, so again, I do want to be clear that we have not really looked at anything that has an input, of the inputs to the system and the present state. So if I know the present state, then I can determine the next state. So I know what the next state is going to be. Okay, and then the other thing is they're finite. The number of states is finite. I have a limited number of states, so there's not like a crazy universe of possibilities out there for me in my state machine. I just have this limited number of states. So this is all very abstract, and I want to do an example sticking to a counter, so simple counter like what we've been doing before, except this one is going to be a little bit different. So let's do an example, and we're going to do an up and down counter. So what does that mean? So the operation of the up and down counter is that I have an input X. So this is new. We haven't looked at anything that has an input yet. So this counter has an input X, and when X is equal to 0, it counts up. It's an up counter. And when X is equal to 1, it counts down. I mean, you could do it the other way if you want it. It doesn't matter. But that's the way we're going to do it. Okay, so what's the first step that I'm going to do? First, let me give you a little bit more information. So my information is it is going to be a mod 8 counter. So what's the first thing that I need to do? So the first thing I'm going to do is a state transition diagram. So my step 1 is the familiar state transition diagram. So I'm going to list all my states. Now, when I talk about states, what am I talking about? I'm talking about my counter output, okay? So I'm just talking about my counter output here, and my counter output. So I said it was mod 8. So how many flip flops do I need, or how many bits do I need? Mod 8, 3. So first, let me write all my states. Okay. Now I have to indicate the transitions between them. But the transitions, so up until now, I've only ever been talking to you about unconditional transition. So what is an unconditional transition? It means I go from state to state like clockwork at the edge of the clock. So always when I talk about my transitions, I'm talking about synchronous transitions. They go with the edge of the clock. But this is slightly different. So they will still go at the edge of the clock. I will still transition only at the clock edge, but I have something new here. Okay, so now what I need to do is I need to specify my conditional transitions. So my transitions, whereas previously they were unconditional, now they're qualified. Okay, so I'm going to start it off for you. So I will transition, if I'm in state 0, I will transition to state 1, but only when x is 0. Right? So I'm going to put a little qualification next to the arrow, and that tells me that my transition is conditional. And I'm going to do the same over here. So when x is equal to 0, it's really easy. I'm just counting up. You just have to affix this little label that says x equal to 0. And this tells me under what circumstances I am going to be transitioning. So in general, when I have an input, I am usually going to be transitioning in this case, I am transitioning depending on the value of the input. And I indicate that by writing this, x equals 0 here. And I indicate it by just attaching this little label that says x equal to 0. So now I think you can imagine the way down. So how do I indicate x equal to, like, that when x is equal to 1, I'm counting down? How do I indicate that in the state transition diagram? So I'm just indicating now that my transitions, which are the arrows, between states, which are in the bubbles, now they are no longer unconditional. They are conditional on, and they're conditioned on the value of x. So what are they dependent on? What are they conditional on? The value of x. So when I'm talking about x, I'm talking about an input. When I'm talking about an input, what does it really mean, like on a breadboard? What's an input? Maybe it's a switch. Maybe it's the output of another logic circuit. Whatever it is. So it's some kind of input into my system coming from somewhere else. So whether that somewhere else is me manually pressing a push button or flicking a switch or a dip switch, or the result of another logic circuit. That's what my input is. And again, I'm not talking about, I actually want to be clear here that I'm only looking at one aspect of a state machine. So we have just had these, unconditional counters that count in different counting sequences. And now I'm adding one piece to the sort of like the front of it, which is the input. But I'm also going to add on later, to give you a little teaser of what's up ahead, I'm also going to add an output. So really, like right now, the outputs of my state machines are just the counter outputs, the states of all the flip-flops. And that's the counter output. But eventually I'm going to want to transform that into something more interesting, right? Because like, what am I going to do with a counter? But eventually I'm going to transform that into something that's more meaningful. So we'll have much more complex state machines. But I want to start slow because it's really important to get the basics before we move on to the more complex stuff. And if that wasn't clear, don't worry, but we're adding in this input component, and we will be adding outputs. So we'll transform the state of the counter into some other kind of output. Okay, so what's the next step after this? Excitation table. Okay, what's this going to look like now? What is my excitation table now? So my excitation table up until now has assumed that my next state is dependent only on my present state. But now I have this extra variable x, right? So my excitation table is now, recall, I'm leaving room on the left. So if you're copying this down onto paper, leave some room for yourself on the left-hand side. So this has been my normal, my up until now, my regular excitation table where I've had present state and I've had next state and I've had control inputs. And my present state were basically my determined by the values of my flip-flops. And my control inputs were dependent on the type of flip-flop I was using, which I haven't determined yet, so I'm going to leave that blank. But for D flip-flops, I would just have 3 of them, 1 for each flip-flop. And if I'm using JK, then I have 6 of them, 2 for each flip-flop, the J and the K. But now I have something else. Input. And I called my input X. I had to give it a name, so I'm calling it X. So I could have called it switch or, up, down. And maybe you want to give it a more meaningful name, but I just called it X because, I don't know, it was simpler. So I'm going to draw this line here. And again, I'm leaving control input, so I will take a vote. You guys get to choose your own adventure. Do you want to use D or JK? All right, let's use JK. And I'm going to fill it in. So I have basically 4 variables that determine my next state: X, Q2, Q1, Q0. And I'm going to fill them out like I would fill out a traditional truth table. So I'm just filling this in like a regular truth table. Why am I doing it this way? Because I'm going to do K-maps for this. So now what do? I need to fill out my excitation table looking carefully at my state transition diagram over here. Okay, so I will start with the case where X is equal to 0. Okay, that's the first 8 rows over here. So if you go look at the first 8 rows over here, that's the case where X is equal to 0. My input is equal to 0 and I'm counting up. That's this. Okay, how do I fill this in? So let's do a couple of rows together and then you guys try to do it on your own. Okay, so I'm going to start with x2, x1, x0 equal to 0, 0, 0. That's this over here. Okay, and I'm going to look at the case where x is equal to 0. And when x is equal to 0, I see that my next state is just 0, 0, 1, right? So I'm going to fill that in over here. So I see that in the case where X is 0 and my present state is 0, 0, 0, the next state is just going to be 0, 0, 1. Pretty simple, right? So this is why I've been stressing up until now that it's really important to follow the state transition diagram. Okay, so what about the next one? When my state is 0, 0, 1, and X is equal to 0, my next state is going to be 0, 1, 0. That corresponds to this row. My state is 0, 0, 1 over here. My input X is 0, and that makes it so that my next state is going to be 0, 1, 0. So I can see from the state transition diagram, and now I'm filling this out, when my present state is 0, 1, 0 and X is equal to 0, my next state is going to be 0, 1, 1. I didn't have to consult the state transition diagram for this because, it's pretty obvious, but it's basically this. When my state is 0, 1, 0 and X is equal to 0, my next state is going to be 0, 1, 1. So now I'm going to fill that out. And then when my present state is 1, 1, 1 and my input X is 0, then I'm resetting back to 0. So I'm really operating, up until here, I'm really operating like if I was just looking at this part of it, I'm really just operating like a straightforward up counter. And now here, I'm just operating like a straightforward down counter. So and again, I'm trying to instill in you this respect for the methodology. Why? Because it may seem very easy when you're doing it for like a very simple state machine, but when we get to much more complex state machines, I really need to be able to follow off the state transition diagram. So over here, my present state is 0, 0, 0. And when my input x is equal to 1, I see from this arrow that my next state is going to be 1, 1, 1. And that's what I write. When my present state is 0, 0, 1, and x is equal to 1, my next state is going to be 0, 0, 0. So that's this row over here. So now I would like you to fill out the control inputs. So again, what am I using to fill out the control inputs? So let's do the excitation table for a single JK flip-flop. Okay, so now that I am doing my present state and I'm trying to determine the control inputs, I really only need to look at present state and next state. I don't need the input anymore. I used the input combined with the present state to derive the next state. And now to derive the control inputs, I need to look at the present state and next state. So this is exactly the same as what we've been doing up until now. So I always start flip-flop by flip-flop. So I look column corresponding to Q2, then the column in the next state corresponding to next state Q2, and now I'm going to look at J2 and K2. So I see that over here I have a 0, 0 transition that corresponds to 0x. Okay, so now I'm going to erase my JK flip-flop excitation table. Why? Because what is my next step now? Like, what was the whole point of this excitation table, really? K-maps. Okay, now what are my inputs to my K-maps? How am I going to write my K-maps? I am going to do the schematic because I want to show you how the schematic looks. Like if you were to implement this in multisim or on a breadboard, what it would look like. And this next thing I'm going to do after that is I want to show you the block diagram. Okay, and the reason I stress the block diagram is block diagrams become very critical. Okay, later it's going to make your life a lot easier if you know how to do a good block diagram. So, schematic. Okay, so I'm going to start off with how many flip-flops do I need? I'm going to assume that you all mentally said 3. Okay, and I am going to specify, I'm not going to show, it kind of crowds my schematic when I show the asynchronous inputs. So I'm going to write them up here. So my asynchronous inputs are active low. And for the JK flip-flops that you guys have, they're called preset and clear, or R bar and S bar, I can't remember. Anyway, so they're either called pre or clear. In any case, they are functionally equivalent, and they are both active low and asynchronous. And so I want them inactive. This is fully synchronous now. Okay, so nowhere did I have anything asynchronous, so I'm going to make them both high. This is also the same as saying S bar equals R bar equals 1. So you'll notice that on some of the data sheets, it's not called preset, it's called set. And on some, it's not called clear, it's called reset. But I want you to understand that they are both asynchronous and they're both active low, either way. So the next thing that I do, what's the next thing that I do? What do I do for a synchronous circuit? So for a synchronous circuit, I make the asynchronous inputs inactive. And then what's the next thing that I do? What's an important thing in a synchronous circuit? I put the clock. And I'm just going to feed the clock. So again, it's synchronous, which means that all the flip-flops are being fed through the same clock signal. Okay? And now all I have left to do is wire up the J's and K's. So in all flip-flops, in this case, J and K are wired together. And in the case of Q0, so I'm looking at this guy now, J0 and K0 are both 1. Now for J1 and K1, again, they are the same, they've got the same logic expression, so I can just wire them together. Now, if I'm doing like a multisim schematic and I tell you like X is coming from a switch, okay? So basically the output of the switch is this, what I've denoted by X here, and the inverted output of that switch is this X bar. And then the other two inputs, so again, what am I doing? I'm doing J2 and K2, which are the same signal. So actually, let me connect them here. This is Q1 bar, and this is Q0 bar. Where do they come from? And this is Q1, and this is Q0. Now, where do these signals come from? So Q1 bar and Q0. Now, they're coming from here. Well, actually, this is Q1, Q0, Q1 bar, and Q0 bar. I could have drawn the arrow, but for the sake of neatness, I didn't draw the arrow. I just labeled it. But you can think of in your head this invisible arrow coming from Q1 and going all the way here to this input of this AND gate. And same for Q0. And and over here for this AND gate, my other two inputs are Q1 bar and Q0 bar. And that's just Q1 bar and Q0 bar. So you can kind of mentally draw the wire in your head, but I haven't done it here just for the sake of neatness for my schematic. So now I have just fulfilled these expressions over here, J2 and K2. So let's do J1 and K1. And again, where is my X coming from? It's coming from here. It's coming from the output of my switch, okay? And my Q0 is coming from here. So it's as if I had a wire coming from here to here, but I just didn't draw it for the sake of neatness. So this is my full schematic to implement my up-down counter. You recall the famous block diagram. Some people get confused about terminology here, but the block diagram is literally blocks. That's why it's called a block diagram. So I'm going to show 2 blocks. We're going to add another block, not today, but in next class actually. So one of my blocks, remember this? Memory, which is basically flip-flops, but I'm calling it memory. I'm giving it a fancy name. So remember that my other block was the control logic. So the control logic is this stuff over here. This is all control logic. These gates, it's just purely combinational. I don't have any clock input, so there's nothing sequential about it. It's just combinational, okay? And in fact, this wire could actually also be considered part of the control logic if you really wanted to be pedantic about it. So control logic, purely combinational. However, my memory, flip-flops, is not. This is sequential. It needs a clock input. So the clock input only goes to my flip-flops, not to my control logic, which is purely combinational. And the idea behind my control logic, I'm not going to show all the wires. Okay, I'll show all the wires. The idea behind my control logic is that it takes in the present state, which is given by the Q outputs of all my flip-flops. Okay, and actually, I'm going to just extend it out here. So I have the outputs of my system are simply the counter states. Now that is not always going to be the case, as we're going to see next week. And the inputs to my control logic are also just the present state. So the purpose of this control logic block is to take in all the present states and spit out the control logic. And the control logic is what? It's the J's and K's. So its purpose is to spit out all the control inputs that are needed to make sure that the flip-flops get to the correct next state, the one that I want. So each wire is actually 2 signals, but anyway, just bear with me. It was simpler. Okay, but what am I missing? So this is very similar to or identical to stuff that we've seen before, but I'm missing something. What am I missing? What other input do I have? I'm missing X. Where does X go? What is it an input to? Look at my schematic. What's X an input to? The control logic. And voila, that is it. Now, I'm making a big deal about this X and these block diagrams because you're going to see that there are very subtle variations of this that may have very large effects. Okay, so I want to start with something simple, understand what inputs go where, into which block, and then we are going to build on this and we are going to make some very complex systems, but we're going to use this as a basis. So I hope everybody was clear on this. This was the class.